You all can see it's from the TimescaleDB, and so yesterday and today morning, Ajay gave the introduction about how Timescale is managing the time series database and the numbers and the performance numbers and everything. Today, Matt will walk us through like what exactly they did to achieve this kind of scales and numbers. So I hope it's going to be exciting. Matt. So Matt work as a core software engineer at TimescaleDB, and he is a PhD. Uh, I'll hand over to Matt.
Hi, thank you. So, hi, I'm Matt. I work at TimescaleDB as a software engineer. TimescaleDB TimescaleDB is an open source database extension to Postgres available on GitHub. We have been around for about a year. We have about 4,000 stars. Actually, let me pause. Can I see a show of hands of the people that were not at Ajay's talk yesterday? Okay. So I'm going to go through the stuff that was covered yesterday a bit quicker so we can get to the technical meat a bit faster. So in truth, we are a database that recently got funding, about $16 million. And that funding, we got it because time series data is starting to emerge everywhere. These are just some of the verticals where we are seeing it emerge. Industrial machines, transportation, data center ops, and financial. And the question is why? Well, I believe the reason that time series data is starting to emerge in so many places is that in the past, we were constrained by the power of our machines. And so we were able to only store the last state of our systems. For example, in the financial settings, so we were able to store only the bank account balances. As databases grew more and more powerful, we could afford to store more stuff. And so then we started storing the entire history of all of our transactions. So now you get, double entry bookkeeping on the computer level, right? But now, in order to make use of more and more customer data, businesses want to actually store every interaction a user has with the system so that they're able to get the most kind of business analytics out of that information. And so what they want to really store is every time the user logs in, information about that. It could be as fine-grained as, where the mouse on the web page moved at a certain points in order to find out the hot spots of a banking website. And so this is really a lot more data. And this is all time series data. And so an actual question you might ask at this point is, what is time series data? And if you come from the metrics world, or from the kind of a sysops world, what you have been told is that time series data is something that has a name. For example, CPU is associated with a set of tags that describe where that data is coming from. And then the series itself is a combination of time and value pairs, where the values are usually strings. So for CPU, it could be like a timestamp and the amount of CPU. And then you would have multiple of these time series, right? And so then the people in the metrics world start talking about the number of time series you have, right? And we believe this is all wrong. So what we actually think is that instead of storing these time series independently, what you should do is if you should store all of the data you collect together in some kind of combined entity, so you have semantic knowledge of the fact that this data is combined in a certain way. So instead of having CPU and free memory and temperature being separate time series, you store it in a row format, which kind of gives you the relationship between these things. And when you do that, you are obviously able to then ask more interesting queries, like what is all of the data that I collected at a certain point of time? But even more interesting, what was my free memory doing when my temperature was above 100? Or when my CPU was above 100, already you get a lot more contextual information this way. You could also then do more interesting things with group bys by, for example, grouping by a bucket of CPU and seeing what your free memory was doing there. But in a more general sense, you have some kind of information about the correlations between these things now, which allow for much more complex analysis. And so before I showed you kind of this view, and the tags were still kind of the separate entity living by itself. But actually, you get a lot more power if you take those tags and you convert them to relations where you have a foreign key in your time series data to that tag. Because now, instead of just knowing the name of the region, you now have the foreign key to the region table, which gives you, again, even more information. For example, the region could now have a GPS location associated with it, or some other metadata about the cooling system or whatnot. So in general, time series data now starts to look a lot more like the relational data we are all used to from Postgres. And you might then ask, how is this different from simply any table that has a timestamp in it? And it's not that different. But the only difference is that really this is not the update-heavy OLTP workload you are looking for. Instead, this data, all of the changes are marked as new rows in your table with a new, more recent timestamp, or mostly more recent timestamp. You might be backfilling some data, but for the most part, your data comes in as new data. And this is actually our much broader definition of time series data. It's time series data with a timestamp that kind of comes in over time. So I would argue that almost anybody in this room, even if you don't know, has data like this, because anytime you do an update on your database, instead of updating in place, you can now just insert a new row, which often already happens in auditing or logging tables with triggers. But then, so we've seen this data as a relation, and you might ask, is most of it stored in a relational manner? And this is the results from Pocona of last year, asking people how they store their time series data. And it turns out that about 30% store it in the relational database, while about 70% store it in the NoSQL database. And the question you should be asking yourself is why? Why, if you, as I just showed you, you get a lot more power from a relational representation. Why don't people store it in a relational database? Well, the answer is all about insert performance. And if you run an experiment where you insert data continuously into a relational table, when your data set size is small, you get pretty good insert performance. But as your data set size grows, your insert performance kind of becomes really bad and really variable. And the reason is that you're now swapping in and out of disk. So what happens is at the beginning, most of your working set fits in memory. As your working set no longer fits in memory, you have this pretty horrendous performance degradation. And it's very easy to kind of wave your hands and say, well, you now have swapping in and out of disk, and so this is bad. But let's see exactly what happens when this behavior initiates. And so I'm going to show you a very simple B tree. This is, from Database Systems 101, where I'm now inserting a batch of three tuples into the B tree that's already partially full. So in this example, I'm going to have only enough memory to store 2 nodes of your B tree in memory. So when I insert the first tuple, the 5, which needs to go into the, I guess it's going to be the left-hand side, all you do is you load up the path to that leaf in memory, and you insert the 5 in memory, and that's it. You don't have to do anything else. But now when I want to insert the 17 into the middle thing, now I don't have enough memory to just load the middle leaf into my into memory. So now I have to swap out the leftmost leaf back to disk. So that's right. And only then do I swap the middle one in, which is another read. But then now, when I have to insert the 8 again into the leftmost leaf, I have to do this again, which means I have to swap out the middle one and swap in the left one. And so I did 3 operations. I have 6 IOs. And you might say a doubling is not bad, but this is actually proportional to the height of your B tree. So the deeper your B tree is, the more of these swappings in and out you have to do, because then you have to swap in and out the entire path to your node. So this gets really bad really quick. So to summarize, the reason that traditional B trees don't work very well is because as your table grows large, and now your B tree is no longer fit in memory, you have to do a lot of swapping in and out of the disk. So then you might ask, well, NoSQL kind of solved this for us. This is the exact pattern they were optimizing for. So why not just use that? And there's a lot of NoSQL systems around there, but I'm going to talk about the ones that use log structured merge trees, which is the vast majority of them. You could see the list here. And a log structured merge tree was really invented to do efficient key value stores. And the trick that it played was that all of your writes were written to a table that were then periodically swapped out to disk, so you didn't have the swapping behavior. And let me show you more particularly what I mean by that. So in a log structured merge tree, you have a mem table which lives in memory, and a list of SS tables that are on disk. And what happens is when you insert a batch into your system, you first insert it into your mem table. When your mem table fills up, you will sort the entire mem table and write it all to disk as one operation, which actually solves the problem that I was describing with the B trees before. However, this works well with a key value store, because the logic in a key value store is you have a key, say the number 5, right? And what you actually do is you start looking at the newer SS tables, searching for the number 5. Once you find it, you are done, because you can stop your search. You don't need to look further back into previous SS tables. However, if your key is now a time, and you're looking for information within the time range, you can't play that trick anymore. So all of your scans will have to go through all of your SS tables back in time, which is now much less efficient. And there's a bunch of tricks people play to get around this. Some of those tricks are about merging the SS tables in the background. Some of them are others. A lot of the tricks people play is they keep auxiliary in-memory data structures to efficiently map text to keys. And this sounds great because it could now give you some efficiency on the query side, except that the way these data structures work is that you have to store the entire cardinality of the tags that are associated with your time series. And if you want to store fine-grained information, this grows very large. And now you need a lot of RAM in order to do this efficiently. So that's the first problem with key value stores. The other problem, so let me ask you this as a Postgres audience. Can you cluster in more than one key on Postgres? The cluster command. You actually can't, and this is because clustering, just like log-structured merge trees, it needs to order all of your tuples, and you can only order your tuples in one way. There's no way to do it multiple ways. So fundamentally, this data structure doesn't really support multiple indexes like you have in Postgres. And so the way people have dealt with this is that they put these tags again that I talk about in time series data as part of this key. The problem with that is that now at write time, you are deciding what is the most efficient way to query your data, because there's no other efficient way to query your data. You cannot have a secondary index. And that's all to say that you give up a lot of power when you go from Postgres to NoSQL with log-structured merge trees. And you give up the power of secondary indexes. You give up the power of more powerful performant queries. You lose consistency guarantees given to you by JSONs. You have no joins, and you don't have SQL. So this is quite a lot to give up. And then we asked ourselves, is there a better way to do this? And this talk would be really boring if now I told you no. So of course, there is a better way, and we built it. And we built it as a Postgres extension. And on a high level, kind of the basic idea is that timescale allows you to store time series data in Postgres efficiently, and so you get to keep the entire power of SQL, the consistency guarantees associated with Postgres, but we allow you to scale the system to hundreds of billions of rows. And another benefit is that we inherit the reliability in Postgres. So how do we do this? Well, time series workloads are different than the OLTP workloads presented that Postgres was built for. And the way in which it's different is that it is not updates. It is primarily inserts, so we could optimize for inserts instead of updates. And the writes are not randomly distributed. They are kind of, as I said, they are really concentrated on the most recent time interval. And so we could leverage these differences to make B trees and Postgres work. The way we do this is if you imagine this as your time series data coming in from different locations over time, what we could do is we could partition this data by time. And further, we could partition this data by what we call space. And that's really very often, although it doesn't have to be, it's an identifier that shows where this data is coming from. And then each of these subspaces in this partitioning becomes what we call a chunk, but that chunk is actually implemented as a Postgres table. And we call the entire collection of chunks a hypertable. It's somewhat similar to the parent table in a hierarchy with some differences. And this hypertable gives you an abstraction with which you interact with it in terms of SQL. You can insert directly to a hypertable. You can select directly to a hypertable. You can define indexes, triggers, constraints on the hypertable. You can do table management commands like vacuum and cluster on the hypertable and not on the individual chunks, etc. You might say, well, we have something like this with Postgres 10 partitioning, but it turns out that if you have Postgres 10 partitioning and you try any of these things in the red on the parent table, they do not propagate as you would expect to the child tables. So there's a lot of manual work involved in doing this. And what I would point out is that upsets, which is on conflict clauses in Postgres, you can't do that at all in Postgres and declarative partitioning. The upsets are very common in time series data because time series data are often measurements coming from somewhere. You might want to like repeat the measurements. So on conflict do nothing is a very common and natural thing you would want to do. And you can do it with us and you can do it with Postgres and partitioning. We also do automatic space-time partitioning. So like declarative partitioning, when you insert to our hypertable, we will route the tuples to the appropriate chunks. And the way we do this is by analyzing the appropriate attributes or columns in the tuples and deciding which chunks correspond to that, because all of these chunks here are kind of disjoint in the partition keys they operate on. And we have put in a lot of work here in order to optimize this process by caching information about chunks internally and having specialized data structures to do this lookup very efficiently. In addition, when your chunks kind of fill up, and this often happens with time, right? You are now trying to insert tuples for times that haven't previously existed. We will automatically create the chunks for you for new time periods and the route to them. There's a bunch of chunking benefits. One of those benefits is that chunks are right-sized. And what we mean by that is that we size the chunks so that the indexes belonging to an individual chunk now fit in memory. And this is exactly what allows us to get around this problem of B trees swapping in and out of memory, because most of the time you're writing to recent chunks, and if the recent chunks now fit in memory, it doesn't matter what your data set size for the rest of your older chunks was, because they don't need to live in memory now. And now your B tree lives in memory, and you avoid this swapping behavior I described before. Another advantage is that now you could distribute these chunks across disks, and and we support that. Either you could use a RAID setup or you could use table spaces in Postgres. One of the major advantages of this now is that you can add disks as your data size grows. This is especially great on AWS or Azure or any of the other cloud providers, where you can dynamically just attach SANs or block devices. And this allows for faster inserts because you're now parallelizing your I/O across different disks. And for the same reason, you can now parallelize your I/O across queries. And if you kind of squint your eyes hard enough, you could replace these disks at the bottom with actual nodes. And you could imagine how this would work in a scale-out environment. We don't yet have this. Right now, we are a single node database, just like plain Postgres, but this is an active development right now, where we would allow you to spread your chunks across various nodes in order to scale out. Another benefit of chunking is that you could use it for retention policies. Often what you want to do is you want to keep the latest month of data and drop data as it becomes older and older. Now, a natural way of doing this in Postgres is with a delete operation. But the delete operation is expensive and incurs a lot of vacuuming costs. Instead, if you partition your data by time, what you can do is just drop entire chunks as they become too old for your retention policies. And actually, a chunk drop, just like a table drop in Postgres, corresponds to a delete of a file on the file system, which is a very efficient operation. On the query side, what you can do is you can leverage Postgres constraint exclusion to figure out from your query which of these chunks you need to touch, so you avoid chunking all of them. So, for example, if you partitioned your data in terms of space by device ID, and the spatial partitioning is hash partitioning in our system, what you can do is when you query for a particular device ID, you don't need to query the chunks that correspond to other hash partitions that can't possibly have that device ID. And of course, you can play the same game with time, and only query those chunks that are most recent to that fall within the time range you are looking for. And this is actually also very powerful for geospatial queries, because geospatial queries don't use B trees, they use just indexes. This is a way to kind of add another method of exclusion to your geospatial queries, because just indexes don't support the multi-column indexes, so you can only index by the geography column, if you will. And so if you have these other partitioning types that's kind of like a secondary index on those type of queries. But we couldn't just rely on plain constraint exclusion, and I'll show you why. So let's say we have a very simple select query where you do a where clause where time is greater than now minus 24 hours. Can anybody tell me why, I guess I gave the game away, why this would not work under Postgres native constraint exclusion? Yeah, it won't exclude it, but why? Yes, so the first thing is that the semantics for that now has to evaluate the execution time, so the planner can't make it a constant. The second issue is that even if it could make it a constant, now is a timestamp with time zone, and that's evaluated based on the time zone setting of your Postgres server at the time of execution. And if you have this in a prepared statement, you might change this setting since you prepared it, so you can't decide what to do at planned time either because of that reason. And so in plain Postgres, it won't exclude this chunk. It won't exclude chunks based on this. What we did is we added additional constraint exclusion that happens at execution time instead of at planning time, so that you would avoid this kind of problem. I talked a lot about performance, but there are more reasons than just performance to use TimescaleDB. One of the main reasons is that you can simplify your stack, whereas before you had to have your relational data in one database and your time series data in NoSQL. Now you can combine it into one. We also added a whole bunch of new functions to make time series analysis easier, including time bucket, which allows you to do the equivalent of date trunk, but for, say, 14 days instead of just at the day, month, hour granularity. We also added some aggregate functions that allow you to do last and first ordered by time, which is different than min-max because min-max orders by value, but here you want to get kind of the value ordered by some other value, which is time often, but it could be something else as well. So there's a whole bunch of these things that we've added that you can see in our docs that make the analysis easier. Another thing that you can do is you can do data retention and aggregation. So often what you want to do is you want to kind of keep raw data for a week, then aggregate it together and keep the aggregates for a month, and then aggregate it even more and keep it for even longer. And you can actually do this right now in our system with regular SQL queries that will aggregate your data as you would expect and put it into another hypertable scheduled over time in cron or something like this. We're actually right now in active development on making it a lot easier for you to do it. So this is a great way of speeding up your queries and keeping data at different granularities. And of course, the major advantage probably is that you now speak Postgres. And so all of your toolings, Tableau, Power BI, Grafana, will just work as you'd expect because the hyper table I was talking about looks just like a regular Postgres table to both the user and obviously any other tools outside. So the performance benefits. This is the graph I showed you before with plain Postgres in blue kind of falling off a cliff in the performance. Timescale here is in red. And so this kind of partitioning actually works to keep your your performance consistent. This is up to 250 million rows because running Postgres beyond that just took too long. This is for single row inserts, and we get 14,500 rows a second, which each row in this experiment is 10 metrics, so you get 144,000 metrics a second. Once you go to batching, the cliff of Postgres is even more apparent in a way, but you get much higher performance overall. So we're able to get over 1 million metrics a second being inserted at a batch size of 1,000. And you can see timescale is performs well up to 1 billion rows. This is parallel. Yeah. Whether the answers were sequential or parallel. In terms of queries, oftentimes we get similar performance to Postgres, but on very common queries for time series data, we get a lot better performance, up to 10,000x in time-ordered group by queries. And as I mentioned before, because we drop chunks instead of deleting, our deleting of old data is also a lot faster. So, but you might ask, why is it that you're able to get this kind of performance improvement? And the reason is that we go from a sequential scan to an index scan. And let me give you an example. So say you have a table with a time column on it. And now you want to, aggregate it according to the minute of time that you have. Now, will Postgres use this index for this query? It won't, and why? Yes, because there's a date trunc function that messes up the information. And the fundamental reason why the date trunc function kind of doesn't allow you to use the index anymore is that now Postgres doesn't know anything about the ordering properties of time with relation to date trunc of time. And these ordering properties are very important because they determine when an index order can be used to fulfill a query. Inside the planner, these are called path keys. They are what determines the ordering of your query, and then you compare that to the path keys of your index to determine that it's the same kind of ordering. So what we have done is we have created a kind of admittedly very simple algebra that allows you to convert path keys from your queries to path keys on the underlying columns for certain functions. First of all, like date trunc, like time bucket, and a few others, but also on mathematical functions. So if your time is in terms of integers and not in terms of timestamps, which we also allow, it could also reason about which mathematical operations will allow you to preserve the order. And we have, in our code, if you read it, we have a whole bunch of proofs right there in the code that the algebra is sound and that this is correct. But the basic idea is that we are able to reason about transformations on columns in terms of the ordering guarantees they preserve. So anybody who's followed this would ask about Postgres 10, because Postgres 10 really did have a lot of improvements for performance of partitioning in terms of ease of use and in terms of performance. And more of this is going to come in Postgres 11. It's actually quite exciting because Timescale will be able to leverage those improvements as well. But one of the problems in Postgres 10 declarative partitioning performance is that declarative partitioning was still designed for the OLTP use case. And in the OLTP use case, you might have 40, I don't know, 60 partitions is very high for an OLTP workload. But for time series workload, because you partition on time, you kind of add in the partitions ad infinitum. And so we have had customers with 5,000 or more partitions. It's not that uncommon if you are, say, adding a partition per day, right? And on the insert path in Postgres 10, there's still kind of locking and or opening of the underlying tables. And so this kind of the insert performance degrades the more and more partitions you add. This is the basic thing. So locking and opening of the underlying partitions is one problem. The other problem is that they do not do the kind of caching things that we do with regards to information about their partitions. And so there's still a major improvement on both single row inserts and batch inserts. Obviously on batch, because you are amortizing the cost of the opening and locking of the underlying partitions, Postgres does better, but there's still a big gap. Comparing us to NoSQL systems, we compared ourselves to Cassandra, and we find that Cassandra is actually great because it can scale, but its single node performance is not that great. So there's already a big gap in efficiency on a single node when comparing Cassandra and Timescale, and the gap is about 10x. So you can replace a 10-node Cassandra cluster with one of our nodes. And in terms of queries with regards to Cassandra, we also do a lot better, and a lot of it has to do with the fact that secondary indexes in Cassandra are kind of not as well supported as Postgres. They're actually not supported at all. If you want to do a secondary index in Cassandra, you have to reinsert the data because remember I mentioned that you can only have one ordering in your index in a large structured dimension tree. A similar thing happens here. As I mentioned, timescale is very easy to use, and that's because you create a table using regular Postgres. You run the one function to convert the Postgres table to a hypertable, and now you do inserts and selects and all of your other operations as you would a regular table. So there's actually not much training even necessary in order to start using timescale, and migration becomes super easy because if you have a regular table, you can just do an insert into using a select. So migration from a Postgres table to a hypertable is a one-line command. And we are on GitHub. We have issues. We welcome pull requests. We have a Slack channel where you guys can come and talk with us. We actually have quite a lot of activity on Slack, so if you have any questions, chances are that either one of us or somebody else already using timescale will jump in and help. And we're also hiring. We're hiring across a lot of roles, so if you're interested, please come talk to us at the booth.
Okay. Just a second.
So when you've done the benchmarks, you had chosen Cassandra. I wanted to talk about some of the other columnar databases that are there, which are both open source, or at least one of them is open source, the other one was open source. One of them is CitusDB. The other one is InfoBright. So how does timescale compare to them, both from a time series perspective and also because especially if many of the time series data are analytical in nature. So columnar databases tend to do much better in analytics kind of use cases. So do you have any benchmarks or any thoughts where timescale is different or has taken approaches different from these?
Yeah, so there are a few things to say. With regards to Citus, I think we play in quite different spaces. Citus is still optimized for OLTP data, and if you look even at the documentation, it's all about multi-tenancy OLTP workloads, which is what they're designed for. They're not optimized for time series data, so they don't have a whole bunch of the query optimizations. They are inserts. It's just kind of apples and oranges. In terms of columnar databases, what I would say is that the columnar databases do, in fact, do very well on simple column rollups, which is great if you're doing the kind of simple time series analytics I referred to at the beginning of the talk. But if you're doing correlation analysis or any kind of more analytical queries, then you start to see the advantage of a row-based column store. Although one advantage of a column-based store is that it does get better compression. That's, I mean, if you need the compression, then you should definitely, absolutely use a column store. On disk compression, by the way, not in memory. But
do you do any stuff for that, like disk compression? Because time series data also has high amount of repeatability.
yeah,
like for example, if you look at weather data, I think you gave the example of weather data, right? If you look at the station or the ranges are very range bound, right? For example, temperature is again range bound. It probably has maybe 5,000 or 6,000 values they can typically take?
So what we actually find is that you get a very good compression by using the file system compression as Postgres suggests. So if you use Btrfs or you use ZFS with the compression turned on, you get the lowest we've seen is 4x compression, and often a lot more. So on some level, we don't really believe that disk space is a problem, and so we don't want to optimize this. I mean, disk is cheap and memory isn't, so we've been concentrating on that part of the puzzle, if you will. But if you want better disk compression, what we suggest is using one of the compressed file systems.
Any other question?
Seems like your power of performance lies in a chunking logic, like how you chunk the data, and this is how you get a better performance for time scale. So one is it something your proprietary algo which does this chunking? Second is what happens if I change my interval over the time? So like I started with 5-minute internal and your chunks are calculated based on that interval, and tomorrow I reduce it to 1 minute, and then I change it to 30 seconds, and I introduce some matrices with different time interval. How this chunking work with different data sets, or if I keep changing my time interval for same data set?
Yeah, so what happens is, first of all, our chunking algorithm is a kind of, is pretty standard partitioning stuff. So most of our value, I would say, is in terms of actual implementation complexity. There's some IP there, but most of it is implementation work. In terms of the changing time intervals, what happens is that when you change a time interval, that new interval applies to new chunks when you create them. And so we actually have a quite complex logic or algorithm to avoid collisions when you change the time interval with already existing chunks to preserve this disjointness property, which we need for unique indexes and upsets and stuff like that. But barring collision issues with the existing chunks, the new time interval will only apply to new chunks. And one of the reasons is kind of this slowdown I showed you before happens on the insert side, on the insert side. So if your data is already in chunks, for the most part, it doesn't make sense to change the interval on all the chunks because the hard part, the insert, has already been done. Now, there is a caveat to that you might want to change old chunks if you are relying on the chunking for constraint exclusion on your queries, in which case, right now you have to kind of create a new hypertable and copy the data over. But if you are dealing with the hard problem of speeding up inserts, then changing the interval will just work.
Okay, something forward-looking. Do you guys analyze the pattern of accessing chunk to resize it based on the user query? Like you know that if I query all the time, these kind of the range queries come, and chunk size, what your logic decided is not optimize that? Do you, based on the user access pattern, your optimizer looks beneath and change it the chunk size or the data within the chunk? Or it's static, once created, you continue with the same chunk size?
So we have a experimental feature to automatically adjust chunk sizes for you based on insert patterns. We have not yet done anything with select patterns or query patterns, but we do have kind of an auto adjustment mechanism for addressing for insert sizes. Yeah, so the reason it's experimental is that automatic sizing works really well if you don't have a lot of backfill. But if you have a lot of older data, it can kind of mess with the algorithm.
Thanks, Matt. Actually, we are running out of time, so I would suggest, like, if any other question, feel free to catch up with these guys. There's a booth outside, so you guys can have more discussion. Thank you. Thanks, Matt.